Hello, everybody. So we are going now to talk about the equations that we can use to estimate the diffusion coefficient, and maybe I can go back to this slide because it gave like a mind map of what we're gonna do. So this is the first equation, which we call the Hirschfelder's equation. So this is the first equation that we use actually to calculate or estimate the value of the diffusion coefficient. And this equation is kind of modification of the kinetic theory of gases. So it's a modern, like based on the modern versions of the kinetic theory that take into account the forces of attraction and repulsion between molecules, which is the main drawback of the equation that we used before based on the kinetic theory of gases. And here we have the Lennard-Jones potential, which is this term. So this term is the term that takes into account the intermolecular forces. This equation is valid for non-polar, non-reacting molecules. So we don't have reactions taking place, and in the same time it's for non-polar. Non-polar means that these are the molecules that don't have partial charges like water. It has partial positive and partial negative because the difference in electronegativities between hydrogen and oxygen. This is the type of system that we can use this equation for. So if you have polar components like water vapor, for instance, or other polar molecules, then this equation is not gonna give accurate results. So this equation is very similar to the previous one. So if you take a look at what we had in the kinetic theory, you will have Avogadro's number power half, T power 3 over 2. There are sigmas at the bottom, which is sigma A plus sigma B over 2. We have molecular weights here. So it's almost it has some similarities in many terms. So this term is the same, the T is the same, the P is the same. Sigma AB is, as you see here, it's sigma A plus sigma B over 2, which is exactly this. So this is the same as the other equation. So this is the main addition to the equation. These might be just some collection of all the constants. This might be it. So I don't know exactly, but this is my expectation. But at the end of the day, we have almost all the parameters that we have here are understood and known. You can tell at what temperature and pressure you want to estimate the diffusion coefficient. You can tell what are the molecular weights of the two species that you have in your system, but still we don't know how to deal with these two terms, the sigma AB and the omega D. So sigma AB is the collision diameter, and this is an angstrom. So to get sigma AB, I have to calculate it based on sigma A and sigma B. So I have to know what is sigma A and sigma B and get these values. So these are two parameters that I have to get. And by the way, this is something that we will see a lot in all the equations that we are gonna talk about, which is that you will use an equation that includes some parameters, and to get these parameters you have to get them using other equations, and to get the other equations you have to get something from tables and stuff. So you are going step by step until you fulfill all the parameters that you have. Requirements to calculate these parameters. So this is the same here. So we have sigma AB is calculated from sigma A and sigma B. So I have to know where can I get the values of sigma A and sigma B. The omega D, which is the collision integral, is a function of kappa T over epsilon AB. So kappa is Boltzmann constant, T is the temperature, epsilon AB is something that I don't know, but sigma AB or epsilon AB is the energy of molecular interaction. And this is what we said, that this term takes into account the interaction between molecules. So this is the energy of molecular interaction for binary system AB. And this is function of epsilon A and epsilon B. So you would see that here we have some parameters that we need to know, which is epsilon A, epsilon B, sigma A and sigma B, plus the type of relation between omega D and the kappa T over epsilon. So let's say I know the kappa T over epsilon AB. What will be the value of omega D? I must know what is this relation. If this is, let's say, 1, what is the value of omega d. So this is one more information. So we have 5 information that we need to get. And this is what we will discuss in the coming slides. But before we move to the next slide, it's important to notice that this is this equation is or contains units that are not homogeneous. So you'd see that the sigma AB is in angstroms. You'd see that omega D is dimensionless, epsilon AB is in ergs. So the units, and at the end you're getting DAB in centimeters square per second. My expectation is that this parameter is taking into account all these units conversions. I'm not sure, but this might be it. But the point which is important to notice is that the temperature must be in Kelvin, P in atmosphere, sigma AB in angstroms. The molecular weights are already, they have the gram per mole. And at the end you're getting DAB in centimeters square per second. So this is how you should substitute, or the units that you should use to substitute in this equation. So back to the parameters that we need to know so that we can substitute or in the equation and get the value of the diffusion coefficient. This table is in appendix K in the textbook. It is a list of the Lennard-Jones forces or force constants, and this is for different materials. I have acetylene, air, argon, and many other things. And the table was long. I just put part of the table so that you can see what or an example of the elements or of the shape of the table. And here you would see this is epsilon over K over kappa. So it's giving you epsilon over kappa directly. So it's not just epsilon. So it's this whole thing, or 1 over this whole parameter. And this is in Kelvin, and this is sigma in angstrom. So if you have your element listed in this table, so it's gonna be a piece of cake. You already have 4 information out of the 5 are known now. If you have 2 here that you know, then you can get epsilon over kappa, and you can get sigma for them. And back to the equations, you can calculate sigma AB, and you calculate epsilon AB over kappa. So this is very, very easy and straightforward thing. So if you know them or you find them at the table, you are 80% done with the calculations that you want to do. But let's say you don't have your elements in the table. No matter how big this table will be, it's not going to include all the elements or all the species in the world. So you might have something that's not in the table. So in this case, you can use some of the relations that were produced to estimate the parameters, the sigma and epsilon over kappa. So there are equations to calculate sigma, which are these 3. These sigma can be calculated based on the molecular volume at the normal boiling point. This can be used to calculate the sigma based on the critical volume. This can be calculated or used to calculate sigma based on the critical temperature and the critical pressure. Whatever the information that you have, you can use to calculate sigma. And the same here for epsilon over kappa. You can use the critical temperature or the normal boiling point. Of course, if you have a value that's listed in the table, it's going to be more accurate, because these are just estimations and these are just empirical relations that are produced based on some experimental data. So it might not be valid or accurate for all the cases. So if you have the table or the element listed in the table, then it's going to be better to go for it. And of course, it's going to be more time saving, instead of going into these equations and getting data to calculate the sigma and epsilon over kappa. So anyway, so now we can get the value of epsilon over kappa and sigma easily, and it's not a problem now. And now we have only one last piece of information that we should know, so that we can substitute in the in the diffusion coefficient equation, which is the relation between epsilon kappa t over epsilon and the omega d. So this table is it says the collision integrals based on Lennard-Jones potential. So you have a column here for kappa t over epsilon. There is omega mu and omega k, which are the collision integrals for thermal conductivity, or for heat transfer, and for fluid mechanics, which is which is not what we're looking for. We have it here in the second column. So this is the value of kappa t over epsilon, and this is the value of omega d that we are looking for here. So just look for the value of kappa t over epsilon, and you'll find the value of omega d. The same here. This is the continuation of the same table. You put kappa t over epsilon, and then find the value of omega d. There is another way of representing this data by using this graph, where you have kappa t over epsilon or AB on the x-axis, and y-axis is the collision integral. Just go for any value. Let's see if I have, let's say 2, then 2 here is 1.1 to 1.2, something around that, and it says here 1.075. So it's also almost what I expected. It's around 1.1, and that's why the table is more accurate, because the scale here is not easy to, or it's not easy to get accurate values from the graph as it is from the table. So this is the relation between the dimensionless temperature, which is kappa t over epsilon, and the collision integral. So now we're done. We can use the information that we have to substitute in the equation and get the value of the diffusion coefficient. One last thing that we can understand or can know from the equation is that we can get a relation between the diffusion coefficient, temperature, pressure, and the collision integral. So we know that from the equation that diffusion coefficient is directly proportional to temperature power 3 over 2, inversely proportional to P multiplied by omega d. From this we can use this, or we can use this piece of information to predict the value or estimate the value of diffusion coefficient at for a specific system at different temperatures and pressures. So you can use this relation to say that DAB at T2 and P2 equals DAB at T1 and P1, and this is multiplied P1 over P2 multiplied by T2 over T1 power 3 over 2, and multiplied by omega d at T1 over omega d at T2. So this is something that we can apply to estimate the diffusion coefficient based on a known diffusion coefficient at different conditions for the same system. So I'll end this video by solving an example just to see how we can use this system. So this equation. So this equation or example says that I want to evaluate the diffusion coefficient of carbon dioxide in air at 20 degrees Celsius and atmospheric pressure. These are all the information that I know, that it's only carbon dioxide and air at 20 degrees Celsius and 1 atmosphere. And we need to compare the values that we get with the experimental values that are available in the appendix. So appendix, we have already checked it before. I think it was before, let me see. No. Yeah, it's this. So we had tables where we have the system, air, ammonia, and here is air and carbon dioxide. So it should be this value here, and I want to compare what I have here with what I get from this equation. So first we will check the tables to see what. Oops, I will check the. I'm sorry. We'll check the tables to see what information we can get. So from the table of Lennard-Jones force constants, we can find that we have air and we have carbon dioxide. So we'll not need to go into or use the tables that we discussed, or or the equations to estimate the values of epsilon over kappa and sigma. So from this we can summarize the values of the epsilon over kappa and sigma for carbon dioxide and air. And then we can use the equations to calculate sigma AB and epsilon AB over kappa, which is going to be the geometric mean of epsilon A and epsilon B over kappa. I'm not sure if this is clear, but I will just zoom in here. So these are the two equations that we're using to calculate sigma AB and epsilon AB over kappa. It's very simple, straightforward, and everything is put in the right units. So sigma A and sigma B are in angstroms already, so I don't have to do any unit conversions. So this is what I have right now, the sigma AB, and I can calculate kappa T over epsilon, which is T divided by epsilon over kappa, so it's going to be 293 divided by 135, which equals to 2.158. Of course, this is dimensionless temperature. The next step is to get the value of omega d, which I can get from the table, which is going to be somewhere here. I have 2.158, so it's between these two values. By interpolation, I can get the value of sigma or omega d, which is this. I know the molecular weights of A and B. So now I have everything. I have sigma AB, I have omega d, and I have temperature, pressure, I have molecular weight. So by substitution, I can get the diffusion coefficient to be 0.1468 centimeters squared per second. So this is the equation, the results of the equation. Now I can compare what I have with the data I have from or the experimental data that I have in the table. So in this equation, or in this table, it tells me that the diffusion coefficient for carbon dioxide in air is 0.136. But this is at 273 degrees Kelvin. In my case, I'm operating at 293, so I have to use this equation to find the value of the diffusion coefficient at 293 based on the value at 273. To do this, I didn't put any pressure term here because the pressure is constant. So I'm now calculating the kappa T over epsilon at the new temperature to get the omega D at the new temperature, which is 1.073. So now I would do direct substitution in this equation to get the value of the diffusion coefficient, which is 0.1549. The value I got from the equation is 0.1468, which is, I believe it's less than 10% difference. It's, I think, 6-7% difference between the two equations, or between the actual value that we have in the table and the equation or the value that we got from the actual value in the tables and the value that we got from the equation. So the equation is kind of nice and is giving some reliable results. Again, this is like a famous equation that we use a lot. And in the next video, you'll see the rest of the equations that we can use for other systems, which are different from the non-polar, non-reactive systems that we use the Hirschfelder's equation in. So I'll see you then, inshallah. Goodbye.